Comets are generally understood as relatively simple objects, ancient ice, frozen dust, and primitive material left over from the earliest stages of planetary formation. As they approach a star, solar radiation warms their surface, producing a temporary glow before they fade back into deep space. That is what astronomers expected from 3I Atlas. However, observations made after December 26, 2025, well after the object's closest encounter, prompted renewed scrutiny, not through a public announcement or press briefing, but within routine internal space weather analyses. In one such assessment, analysts noted an unusual phrase, persistent conductive structures detected along the debris path. The wording itself was notable. Cometary debris is typically described in terms of dust density, gas composition, or dispersal rates, not electrical properties. This raised a cautious but significant question. 3I Atlas may not have simply passed through the solar system. It may have temporarily altered local space plasma conditions. To understand why such a possibility matters, it is necessary to examine how Earth normally interacts with its space environment. Earth orbits within a continuous stream of charged particles emitted by the Sun, commonly known as the solar wind. Under typical circumstances, Earth's magnetosphere deflects most of this incoming plasma, preventing significant atmospheric erosion and surface radiation exposure. This magnetic shield is not rigid. It flexes in response to solar activity and then gradually returns to equilibrium. During geomagnetic storms, temporary disturbances occur, but recovery is expected. In late 2025, however, recovery behavior appeared to deviate slightly from established patterns. Following the departure of 3I Atlas from the inner solar system, solar conditions remained relatively stable. Monitoring stations reported no unusually powerful solar flares or extreme coronal mass ejections during this interval. Despite this, space weather satellites detected persistent electromagnetic coupling within Earth's magnetosphere. Analysts emphasized that this did not indicate structural failure. The magnetic field remained intact. Instead, data suggested reduced insulating efficiency, meaning energy transfer from solar plasma may have been occurring more readily than expected under otherwise moderate conditions. Importantly, this state appeared sustained rather than transient. Under standard models, cometary debris disperses rapidly and behaves as an electrical insulator. Ice and silicate dust do not typically form conductive pathways across large spatial scales. Importantly, this state appeared sustained rather than transient. Measurements associated with the debris path of 3I Atlas, however, suggested several atypical features. Elevated concentrations of ionized metallic particles, charge-to-mass ratios inconsistent with ordinary comet plasma. Particle alignment correlated with magnetic field lines. Rather than dispersing randomly, portions of the debris appeared organized by electromagnetic forces. Researchers caution that these observations remain under analysis. However, they suggest behavior not commonly associated with known cometary material. 3I Atlas is only the third confirmed interstellar object observed passing through the solar system. Its hyperbolic trajectory indicates an origin beyond the Sun's gravitational influence, making it scientifically significant even without additional anomalies. Spectroscopic data revealed further points of interest. Metallic abundances higher than standard comet models predict. Isotopic ratios consistent with exposure to extreme temperatures. Gas compositions that differ from expectations for pristine interstellar ice. While none of these findings imply artificial origin, they do suggest formation conditions that may differ from those of typical solar system comets. Some researchers have proposed that such characteristics could be consistent with material originating from stellar disruption events. In scenarios involving tidal disruption by black holes or compact object interactions, stellar material can be subjected to extreme ionization, magnetic structuring, and high-energy processes before being ejected into interstellar space. Over long timescales, this material could accumulate ice and dust, potentially masking its underlying properties and causing it to resemble a conventional comet until closer observation. This hypothesis remains speculative, but it provides a framework that aligns with several observed anomalies. Plasma dynamics depend strongly on particle charge-to-mass ratios. Particles with higher charge and lower mass respond more readily to magnetic fields and can form structured pathways under suitable conditions. If sufficient quantities of such particles are present, localized regions of space may exhibit enhanced conductivity. This could alter how energy propagates between the solar wind and planetary magnetospheres. Under this interpretation, 3I Atlas may have temporarily modified the electromagnetic characteristics of space along its trajectory. Trajectory models suggest Earth has only partially passed through the region influenced by the debris stream. As a result, continued monitoring remains important. Observed effects so far, including minor satellite anomalies and subtle navigation adjustments, are not considered hazardous. However, they do fall outside some existing predictive models. This does not indicate imminent danger. It indicates incomplete understanding. For centuries, the space between Earth and Sun has been treated as a largely passive vacuum. Observations associated with 3I Atlas suggest that assumption may be incomplete. If this object represents a broader class of interstellar material, then what appeared to be an isolated anomaly may instead be part of a larger pattern. And science is rarely unsettled by single events. It is unsettled by patterns. If 3I Atlas were an isolated case, it could reasonably be categorized as an unusual but singular anomaly, a comet with atypical composition and unexpected plasma behavior. Science has a long history of accommodating such exceptions. However, anomalies become more difficult to dismiss when they begin to resemble patterns. As post-encounter data continued to accumulate, researchers began asking whether 3I Atlas represented not a unique object, but a member of a broader, poorly understood category of interstellar material. Natural processes rarely occur only once. Meteor impacts often arrive in clusters. Asteroid families trace back to common parent bodies. Solar activity follows identifiable cycles. From a statistical perspective, if 3I Atlas exhibited properties inconsistent with conventional comet models, it raised a measured but important question. What process could plausibly generate more than one such object? This line of inquiry shifts attention away from standard cometary formation and toward more energetic astrophysical events. Gamma-ray bursts are among the most energetic events observed in the universe. They are associated with processes such as the collapse of massive stars into black holes or the merger of compact stellar remnants. While GRBs are most commonly discussed in terms of electromagnetic radiation, they are also associated with the ejection of matter at extreme velocities. This ejected material is highly ionized, often rich in heavy elements, and shaped by intense magnetic fields. Over long timescales, such debris could travel vast interstellar distances. In mid-2025, astronomers recorded GRB 250702b, a long-duration gamma-ray burst originating from the general direction of the constellation Lyra. At the time, it was catalogued and analyzed within standard astrophysical frameworks. Subsequent analysis did not initially link the event to 3I Atlas. However, later trajectory reconstructions prompted further consideration. When researchers reconstructed the inbound trajectory of 3I Atlas, accounting for gravitational perturbations over extended timescales, they noted a tentative spatial alignment with the region of sky associated with GRB 250702b. The alignment is not exact and does not constitute direct evidence of a causal connection. Nevertheless, it falls within a range that warrants continued analysis. Importantly, electromagnetic radiation from such events travels at the speed of light, while physical matter travels significantly slower. This introduces the possibility of substantial temporal separation between the observation of a burst and the arrival of any associated debris. Under this hypothesis, 3I Atlas could represent a fragment of material ejected long ago, intersecting the solar system only now. This remains speculative, but it offers a coherent explanatory framework. If such a connection were even partially valid, it would suggest that interstellar space contains more than passive remnants of planetary formation. Instead, it may include fragments of stellar material, altered by nuclear fusion, extreme gravity, and strong magnetic fields, later modified by long exposure to cold interstellar environments. Accumulation of ice and dust over extended periods could cause such objects to resemble conventional comets until detailed analysis reveals deeper inconsistencies. Before entering the inner solar system, 3I Atlas passed through regions influenced by Jupiter's magnetosphere, the largest and most powerful planetary magnetic field in the solar system. Jupiter's magnetosphere extends millions of kilometers and is highly sensitive to charged particles. As a result, it serves as a useful observational environment for detecting unusual plasma interactions. Archived radio and magnetospheric data from the relevant period have shown subtle irregularities that do not align cleanly with known Jovian cycles or solar-driven effects. These findings are not definitive and remain under review. However, they suggest the possibility of non-standard interactions between the debris field and planetary magnetic environments. If Earth is experiencing moderate effects, Jupiter may provide a magnified reference point. Planetary magnetospheres are typically modeled as semi-independent systems, connected primarily through the solar wind. This assumption underlies most current space weather forecasting frameworks. However, the presence of structured, conductive plasma along interplanetary trajectories could modify this picture. Enhanced conductivity may allow energy and disturbances to propagate more efficiently between regions of the solar system. Such coupling would not be gravitational in nature, but electromagnetic. Under this interpretation, localized changes could produce broader, system-level responses that existing models do not fully account for. Prior to the arrival of 3I Atlas, machine learning systems analyzing large datasets from space plasma observations had identified correlations that were difficult to reconcile with traditional assumptions. These included persistent electromagnetic structures and long-range correlations in regions expected to behave independently. At the time, many such findings were attributed to statistical noise or model overfitting. Prior to the arrival of 3I Atlas, machine learning systems analyzing large datasets from space plasma observations had identified correlations that were difficult to reconcile with traditional assumptions. These included persistent electromagnetic structures and long-range correlations in regions expected to behave independently. At the time, many such findings were attributed to statistical noise or model overfitting. In light of recent observations, some researchers have revisited this data. While no definitive conclusions have been drawn, the possibility has been raised that these systems were detecting real but poorly understood environmental complexity. Not predictions, but sensitivity to subtle structure. It is important to emphasize that observed effects remain limited in scale. Earth's magnetosphere is intact. Atmospheric loss is not occurring. No immediate threat to human life has been identified. What has been observed instead are modest but persistent deviations, increased satellite drag in certain orbital regimes, minor radiation exposure changes in low Earth orbit, navigation systems requiring recalibration. Individually, these effects are manageable. Collectively, they suggest the need for updated modeling assumptions. The primary challenge posed by 3I Atlas is not damage, but interpretation. For centuries, interplanetary space has been treated as largely passive, a vacuum punctuated by isolated bodies. Evidence associated with 3I Atlas suggests that, under specific conditions, Space may behave as an active medium whose properties can be altered by the material moving through it. If interstellar debris shaped by extreme stellar events can traverse planetary systems, if such material can temporarily alter electromagnetic behavior across large distances, and if these objects are more common than currently recognized, then 3I Atlas may represent an early data point in a larger pattern still coming into focus. It did not damage the solar system. It did not trigger catastrophe. It revealed a gap in understanding. And in science, gaps are often more important than answers.